metals, non-metals, and metalloids. We'll call this number 1. So metals. They tend to react with oxygen, acids, and water. So like I was trying to do earlier, we can probably do a single displacement reaction with a couple of these anyway. And that's probably a good review of single displacement. So single displacement means we have one thing by itself and we're putting it together with a compound. We do have 2 scenarios. We're going to deal with the cations here switching around. Gives us B and AC. So that's like scenario. There is scenario 2 where you have the anions switch around. That's not necessarily what we were going to be dealing with here, but that's fine. So there we go. So tried to do this before, where we took sodium in its solid state and put it together with H2O. And I was also mentioning that you got to remember that hydrogen and hydroxide come together to make water. So when sodium goes to knock one of these out, it's actually going to knock this thing out. And we're going to end up with hydrogen all on its own, and the sodium and the hydroxide coming together. Now this isn't the end of the reaction. So you guys need to get used to checking your list of diatomic gases. So remember, when atoms are by themselves, they are either diatomic gases or they're a solid, like that one right there is a solid. And if you check the list, hydrogen gas should be on it, so we can make that one into H2. For the state of the sodium hydroxide, that's where you need your solubility rules, and hopefully you guys have those handy. Hopefully they're on that periodic table. And if you look this one up, hydroxides are insoluble, but this happens to be an exception, so get that there. This was a little tricky to balance, though. Balancing and naming still remaining here. Let's see, we've got kind of 3 hydrogens here, right? We got 2 there and 1 on that side makes it 3. I think my advice is kind of even it out. It's hard to balance something when it's got an odd number. So if I put a 2 there, that actually gives me 4 hydrogens on this side, right? We still have 2 there, and then we have 2 on that side. So I got 4 hydrogens on the right, and only 2 on the left, and so that should give me that. That balances the hydrogens. The only other thing that isn't balanced would be the sodiums, and that would be sodium. So if you had to name this, you would have sodium metal. I was a little picky with the name there. You can call that water. You can call that hydrogen gas. And you can call that sodium hydroxide. I suppose that it's a very similar reaction when it reacts with an acid, and we can try that one next year too. Actually, you know what? It's pretty much the same. We got lots to cover here, so we'll kind of push on. So metals, nonmetals. Pretty much all the opposite properties. They're colorful. They, let's see, do not conduct. They can be any state. Solid, liquid, or gas. We've come across those, haven't we? Like the diatomic gases, or maybe solid sulfur. Maybe liquid, I don't know, bromine, depending on the temperature. And then for your chemical reactions, that's this chemical. Essentially, they're non-reactive. Now, that's not entirely true, but they're fairly non-reactive in the sort of the traditional sense. We could probably figure one out here. In fact, yeah, I got one in mind, actually. I'm just going to move that, actually, so I have some room to do it on this slide here. So chemical, non-reactive. But that more so is, it kind of depends on if it's just sort of individual elements. So what if I gave you, let's see, what if I gave Cl3P2 and we say that's a solid? This thing's all nonmetals, right? Well, first I guess we have to identify what kind of reaction we've got here. And this is the, we only have one reactant. So there's only one type of reaction that can actually occur, and that is our decomposition. Now remember, decomposition is you break it down into its elements. So with this thing, all we got to do is break it down into two elements that make it up. We've got Cl and P making up this particular compound. Now again, we have to consult the diatomic gas list. Is Cl on it? Yes, it is. So it's a gas. Is P on that diatomic gas list? It is not. So we won't put a 2, but we will put it as a solid. Now balancing the chlorines seems to happen a lot where we get 2 on one side and 3 on the other side. 2 times 3 is 6. We want to get 6 on either side. So a 2 in front of that will give us 6 chlorines, and a 3 in front of that will give us 6 chlorines. And I guess we still have to balance that phosphorus, because I guess there'd be 4 of them. There you go. And then naming. Now, don't get fooled by this one. This one's a covalent compound, and we'll talk about the naming in a bit, but this is one where you have to use di and tri to indicate the number of each atom, because you can have like any number of chlorines or phosphoruses coming together to make a compound. So this one's trichlorine, so you name that first one regularly with the prefix at the beginning, and then diphosphide. Chlorine gas, just regular old phosphorus. All right, so after all that, we covered number 1. Yay. And I guess I threw in some bonus stuff for later. That'll make later a little bit easier. So metals, nonmetals, and metalloids. Color your periodic table. That'll help you identify things as ionic, covalent. Have that handy. Have the solubility rules on it. If you can't remember, if you forgot where that periodic table was, it's like you got to go back to like day 1 of our course, or I think it's day 1. Check there. Okay, number 2. Number 2 is, well, we could probably get it done with a series of diagrams here. So I think first thing we should talk about is standard atomic notation. So this will help us cover a bunch of things that we did in the first couple of days. Your classic one might be, we can do a couple here. Nah, I need a little more space. Erase. I do like the fluorine though. Okay. So again, you get this information from your periodic table. F is obviously the symbol. The bottom number here, this is your atomic number. Atomic number. And that tells us one massively key piece of information. That is the number of protons. And this is, of course, how our periodic table is arranged. Hydrogen is number 1, it's got 1 proton. Helium's number 2, it has 2 protons. Lithium's number 3, 3 protons, and etc. And when I guess this atomic number also, if it's a neutral atom, can tell us how many electrons we have. And we'll come to that in a second. Now the other number is rounded slightly. We learned later in the course not to round this, but early on we did. And we called this the mass number. And we found that the mass of an atom is made up of just the protons and the neutrons. We also learned electrons are so light that they don't contribute any mass. So this is our mass number, and it's the number of p's plus the number of n's. So where's all the mass of an atom found? It's found in the nucleus, because that's where protons and neutrons are found. So once you've diagnosed here what you got, your mass number, you've rounded it slightly, you've got your fluorine, you got your symbol, then you can go ahead and say, okay, well, if this is number 9, then it has 9 protons. Frankly, it doesn't say anything about a charge on this one, so we have to assume it has the same number of electrons. And then subtracting will give us our number of neutrons. I guess we could also have an isotope here of fluorine. It can be found in a couple of different ways in nature. So there's these two would be considered isotopes of each other. Not sure I'm going to write that on. Isotopes. Same number of protons, different number of neutrons. So in terms of coming up with our subatomic particles, we have 9 protons and 9 electrons still. Again, no indication of a charge. And now it becomes these two numbers subtracted, giving us 9 neutrons. So you can see that our number of neutrons has changed here. The first example, it was 10. The second example, it was 9. And like I said, those are isotopes. That's the whole definition of an isotope. They have different number of neutrons. And that's why fluorine's mass is like 18.99. It means most of the fluorines out there are like closer to 19, and there's some out there that are 18. Now, we could change this one more way if we wanted, and that would be to give it a charge. So what if I gave you this and gave it a -1 charge? I'll be consistent with my colors here. How about that? I'll do that. Okay, regretting erased. I'm regretting I erased anything. So yet another isotope here. But we'll give this one a -1 charge. The fact that they're an isotope and now it has a charge has nothing to do with each other. I just changed the neutrons just to vary it here. So now it has a charge. Which particle does that affect? Our proton or electron? Well, our protons can't change. Fluorine always has 9, so it's not that one. It has to be the electrons. So this atom started with 9 electrons, and now it's got a -1 charge. So that means it's gained 1 electron. So now it has 10 electrons in total. And to figure out our neutrons would still be those two numbers over here subtracted. So that's 11 neutrons. So there you go. So that's a whole bunch of stuff about standard atomic notation. Now that led us into Bohr-Rutherford diagrams that we'll just briefly touch on. Bohr-Rutherford diagrams. These are probably more important to my grade 12 university students than they were to us, because you learn some rules, different rules than what we learned here. And the 2 rules we learned was that you can have up to 2 electrons in first shell, and then that's full. And then you can have up to 8 electrons in other shells. And that's not entirely true, but for our purposes, it should work out. It works for the first 20. After that, it doesn't work because these rules, this isn't exactly accurate for rules. But it's simple, so. So why don't we just continue with that fluorine because it's such an awesome example. So let's say I asked you to draw the Bohr-Rutherford for that one. You'd say, okay, the nucleus has 9 protons and 10 neutrons. Then you'd say, okay, I have to draw my electrons. I know I can fit up to 2 in that first shell. Bam, I got 2. That leaves me with 7 more, so I can't quite fill the next shell. Booyah, there's my next 7. I guess we also learned about some valence electrons here. Valence electrons. We learned that they do all the bonding. So let's say this. Let's say they are bonding electrons found in the outermost shell. That's a shell, that last word. So with this example that we've got here, we've got 7 valence electrons there in our outer shell. So that would be our number of valence electrons. So I think I asked you guys to say, or just to write it underneath, something like that. We went on to discover that the group number, if you're labeling groups 1 to 8, will tell you the number of valence electrons. And if you look up fluorine right now, it's in group 7. Thus, it has 7 valence electrons. Now, not that we did this at the time, but we can sure do it now. What if we take this same fluorine and gave it a -1 charge? How does that change things? Well, it doesn't change our nucleus. Nucleus is still the same. No, I don't know. Why did I write a line? I've never written a line before. So your nucleus is the same, but what's changed is we've added 1 more electron into that outer shell. So we actually were able to give it that 8th valence electron, if you will. And we filled its outer shell, and that's the whole goal of bonding that we learned in the following lessons, is that atoms aren't happy if they have, half-complete shells. They either want to empty them up or fill them up. And that's what's happened in this example. And that'll sort of vault us into our next part, which is going to be the Lewis diagrams. So number 4, Lewis diagrams. And again, oddly enough, these are much more important to the grade 12 U's than it is to us. But they just show the valence electrons. And we don't need to do an example of all of them, but if you had sodium, it's in group 1, so you give it 1 valence electron. If it's, I don't know, calcium, group 2, you give it 2. Fluorine has 7, so you give it 7. And kind of so on. Now, these ideas led us into discovering how to figure out the stable ions of these different ones, because they're not stable. And we came to discover that metals want to lose electrons. So these two are metals. So they're going to lose their electron and get a +1 charge there. And this calcium, I guess, has 2 valence electrons, so it would actually lose 2. And then we got that fluorine, and it doesn't want to lose 7. We want to take the shortest number here, or path of least resistance. And even in the last slide, we decided that we can add 1 to it, and we'll fill its outer shell. And I'll grab a different color for it. And because we added 1 electron into it, it gave us a -1 charge. So the whole point of this was to figure out what the stable charges of these elements are. And we came to discover sodium's stable charge was +1, calcium was +2, fluorine was -1, and of course the stable charges are just found on the periodic table. You don't have to do these. Are found on the periodic table. So you grab that periodic table and you should be able to find all those little charges. So once we'd established that, then we got into some ionic compound stuff. We'll call that number 5. Ionic compounds. This is one of the reasons we colored our periodic table, because we came to discover that these were made of a metal and a non-metal. That was kind of one way to say it. Another way to say it would be made of a, now metals, they turn into positive cations, so we could say cation here, and an anion. Non-metals turn into the negative anions. So that's really, we're just saying it kind of the same way here. Now, I don't think we'll go through the stuff where we look up the stable charges and we draw all the Lewis diagrams, but we should probably talk about kind of the naming and the crossover stuff for this. So let's say this. To create, this is create an ionic compound, you need to cross over the stable charges. So let's see here. We had calcium from the previous slide, and we determined that it had a stable charge of +2. We had fluorine here, and it had a stable charge of -1. So to figure out how many calciums you're going to make, you just take the number and you bring it down. So, oh, that's a 1. What am I doing? It's a 2 with a 1. What am I looking at? You get 1, but we don't write 1s, right? So then to figure out how many fluorines there are, you look at the charge with calcium, and there you go. And in terms of naming that, it's calcium fluoride. So that was about as basic as these ones got. We can tackle a few harder ones here. What if I gave you this one? Easy enough, I hope. So how many irons are you going to get? Well, we should get 2. And how many sulfurs are we going to get? Well, we should get 3. And when you go to name this one, now this is one of those ones where iron always needs a Roman numeral. If you look on at the periodic table, it's got more than one positive charge. So we could call this iron, what is it? Iron 3, right? It's iron 3. Iron 3 sulfide. The grade 11 university students also found a different way to name this one. You could name this one ferric sulfide. I don't think I made the grade 12s learn about the ick and the us. So don't forget about the ick and the us method here. One of the next things we did was we rolled into some polyatomic ions. So like a hydroxide. Again, we use those in our solubility rules a lot. So when you're looking at this one, how many irons are we going to get? We're going to get 1. How many hydroxides are we going to get? We're going to get 2. And because hydroxide is a little more complicated, I need a bracket around it. So this one is iron 2 hydroxide. I guess if you look this one up on the solubility rules, it says hydroxides are all insoluble, and that's not one of the exceptions, so this would actually be a solid. I guess we did, in the grade 11s, I had you guys cover a couple more things here too with the polyatomics. So for instance, you could have calcium combining with carbonate. And kids, don't forget when the numbers are the same, it's like there's just one of each. So calcium and 1 carbonate. If you look that up on the solubility rules, carbonates are insoluble, and that's not an exception. So that's actually a solid. So that was kind of, everybody learned that. And then I asked the grade 11s, you guys looked at, well, what happens when you change the number of the carbons? So instead of 3, we have 2 in this example. Well, our name changed, didn't it? So the formula is CaCO2. We don't even have that on our solubility rules. You have to look that one up. Maybe I should have named the previous one as well. That was calcium carbonate. And the grade 11s, you guys will be responsible to know what happens when you lose one. And so it actually becomes a carbonite. So calcium Han Solo carbonite. So they're ites, there's some perates, then there'll be a little bit of that. And frankly, when it comes to the exam, like I might just have maybe one question on these ites and eights and per-eights and things like that. So I think that takes us to the end of our ionic compound discoveries. So let's look at covalent, which is going to be number 6. Covalent, made of all nonmetals. Overlap, orbitals overlap. Overlap of orbitals to fill shells. Yeah, save that. So because of this orbital overlap, you can get sort of multiple versions of molecules. So we could get, I don't know, CH4. And so when you go to name this one, I guess this would just be carbon. And you got to realize that we need some prefixes here. We don't start with a mono, though. Mono just can only go in the second one. So you're going to have carbon, tetrahydride. And carbon can combine in more than one way with hydrogen. In fact, you could have C2H6. So the molecule is just more complex here. Now this is where we're going to have to put a di out front. So dicarbon. And then we need the prefix for 6 is, what's that, hexa? So hexahydride. And we can kind of keep going on here. You know, C3H8, etc. Okay, I'll do C3H8. I mean, that's propane, but it's also tricarbon octahydride. Oh, I forgot to mention hydrates. I guess that would have been an ionic compound. My bad. Hydrates, they got water as part of their structure. Right, so there'll definitely be some sections where you guys have to name on this exam or tell me if it's ionic or covalent. It even gets into some of those like bonding types, if you will. Maybe we can mention that here for 7 bonding types. So, you know, it's either ionic or covalent. So if I give, you know, a couple and I say, I don't know, lithium, I don't know, chloride, you know, I ask what kind of bonding type it is. Well, we're looking for that metal. Is lithium a metal? Yeah, it is. So it's ionic. Maybe I got something a little more complicated like C3H6. And you say, okay, well, there's no metals in that one. I know because of my colored periodic table. This one has to be covalent, and it is. And there were a couple of exceptions that sort of came up at this point. For instance, ammonia seemed to cause us some problems. Because, like, when you go to look at this one at first, it's got all nonmetals. So you're like, okay, nonmetals, it's all covalent. But then you're like, well, hang on a second. This was actually +1 and -1, and there was actually some crossover stuff that went on here. So this one's actually ionic. It's got, the bottom line is it actually has characteristics of both. So you would characterize that as both. And I think at this point I always throw in a trick. I'm like, hey, you got argon. What type of bond does it have? Well, it's only one atom. It doesn't have a bond. You know, you need 2 atoms for there to be a bond. So that was some classifying there. Properties of ionic and covalent. I'm like already drained here. I guess that first 15 minutes of rage didn't help. So properties of ionic and covalent here. So when we're talking about ionic compounds, we're talking about, you know, they dissolve in water a lot. They form electrolytes. You know, they're crystalline structures. And covalent ones don't dissolve to form electrolytes. We kind of ended up, and maybe Actually, I sort of just remembered we forgot to talk about something as well. Our trends of the periodic table. I guess we'll have to go back to that. We learned about electronegativity at this time. Electronegativity. And that was a number that shows how well or how strong an atom pulls on the electrons in a bond. En. And we had some kind of magic numbers here, if you will. So when, and actually we did talk about this too in Unit 3, so good recall of that. So when you've got an atom that, when you subtract electronegativities and it's like bigger, it's ionic. You know, so an example would be sodium and chlorine. I'm just looking up, sodium's is 0.9. And chlorine is 3.2. So 3.2 minus 0.9, what does that give you? 2.3. So I mean, yeah, it's like well on above 1.7. So that just tells you it's ionic, and that doesn't really tell you a lot. Again, there's not much interesting chemistry there, just because like you can kind of tell it's ionic because, well, it has a metal. Now it's the other stuff with the covalence where it gets to be a little more interesting. We can determine some things. So when we've got 0, we've got a pure covalent bond, and that's where there is no sharing. And that's where you get your nonpolar molecules. So all the electronegativities cancel out. So that's at 0. And then kind of this range here is your polar covalent. And that's where there is some like electrons get moved around. So you end up with a dipole. And you end up with polar compounds. It's called polar covalent, so I mean, that's probably not a surprise. So I don't know, there'll probably be at least one question on the exam where I give you the electronegativities, and you got to tell me what kind of molecule you've got there. So that lesson's probably worth revisiting, because we did revisit it again. This is totally out of place now, but we never talked about the trends of the periodic table. Atomic radius, AR. Atoms get bigger, you know, going down. They're larger down, smaller across. And there were some reasons here. More shells, more electrons, more shielding. And going across, it was more protons. I think probably I've just, yeah, there's like a question on the exam where I give you a bunch and I'd say which is the largest or which is the smallest, and you just got to use your trend there. We talked about ionization energy, IE, and that's energy required, oh geez, energy required to remove an electron. And that all depended on the size. So it was like the bigger an atom was, the easier it was to take it away. And the smaller it was, the harder it was to take it away. So you can think about your trends for that as well. They're all based on the radius. And the last one's electron affinity. Electron affinity, yay. And this was the energy released when an electron is added to an atom. And this one depended on the size. If it gets closer, there's more energy released. So with the smaller ones, you get more energy released. The larger ones, not so much energy released. And again, your trends fall out. And I think they're all opposite of, they're all opposite. That's supposed to be the periodic table. They're opposite of the radius. So our atomic radius increases that way. And the other two increase this way. And electronegativity actually increases that way too. So that's like I guess it's our fourth trend. It tends to increase up in that direction as well. But you can look that one up on the periodic table. Okay, so wrapping it up here, not really, but we started to look at equations and balancing equations, and I'm not necessarily going to do one of those right now. We've kind of done that all the way along. Eventually, we ended up talking about our fourth, and this is where we will end. What's this, number 10? Chemical equations. There were like 4 types we looked at. First one was decomp. We did mention this one earlier, where you take a compound and you break it up into its atoms, and of course you consult the diatomic gases. The opposite of that would be synthesis. A plus B gives us AB, not A plus B. We already did single earlier, so we'll leave that one off. We did double. This was 2 compounds. AB plus CD. Some of us did a lab on this. Some I'm still waiting on it. And of course, this is where we got into our precipitates. And I think there's a whole section on our exam where I give you 2 ions, and I say, are they soluble or insoluble? You got to decide. So we do have some rules here we need to follow, or signs, I guess, of a double displacement. So 3 signs of a double displacement. The first one was a precipitate forms. So let's see. We got lead nitrate, all nitrates are aqueous, plus sodium iodide. So it's all about saying, okay, well, that means lead and sodium are going to swap places. So that means sodium and nitrate are going to pair up. Now notice I'm not bringing over this bracket in the 2. I'm not bringing this stuff over because that came from the lead. So I don't really care that I just say, okay, sodium is +1 and nitrate's -1. They're each 1. So we actually have the right formula here now. I'm going to erase those. And you go to look up your solubility rules. You realize these are aqueous. And then you got lead and I. Lead is +2. I is -1. So when you cross that over, you get a 2. And you look on your solubility rules, and it's a solid. And I guess we do have to name and balance this one. I'm going to start with the 2 iodines and then the 2 nitrates, and that should balance that one. And of course, I expect you guys to name this. I'll forego the naming because we've already done some naming here. So that would be the precipitate formation. Next one, formation of water. And this is a neutralization reaction, right? Like I spelled neutralization wrong. There we go. So formation of water comes from an acid plus base. Water and a salt. And that is the case because acids have the H plus and a base has the OH minus, and you put that together and you get H2O. So if I gave you HCl and barium hydroxide, again, if you're clever, you can say, well, hang on, I got an OH and an H. That's an acid and a base. It's got to make water. I'm not even going to think about the crazy formula it might make. I just know that it makes water. And then additionally here, we've got barium and chlorine. And then probably some balancing. And then some naming. Hydrochloric acid. Barium hydroxide. I hope at least one person's still listening to me. Barium chloride. Ah. So that's the formation of water, neutralization. So that came up again in what was that? Chapter, Unit 3. Our final one, formation of a gas. Formation of a gas. So this was one where we needed to know stuff. We needed to know that carbonic acid was not stable and is not stable and likes to decompose into water and carbon dioxide. Or sulfur, hydrogen sulfide here. So it's kind of like the same thing, SO2. And then another classic one was NH4OH. Anyway, they all make water, and they all make, whatever else is left over. So it's a decomposition reaction. So we have to keep our eyes peeled for these things forming, when we put the two things together. So if we get an example where we have NH4Cl plus NaOH, well, I hope I made this pretty obvious here. Everything has a charge of 1, which is nice too. You get that molecule, and it's an aqueous, and you get sodium chloride. Now, we've got a couple of aqueuses here. Of course, this is our fourth one, our 3 signs, and then we have, well, what happens if they're both aqueous? Well, it's a no reaction, but this one isn't a no reaction, because I literally just finished saying this is going to happen. So we can take that compound, and in the next step, break it down further, and say it forms H2O and NH3, and then all this other stuff too. And we did have one of those in our lab. And I just mentioned the stuff about the no reaction, so, yeah. So that should wrap it up. Wow, that was a tight 45 minutes. So that leaves you guys with, you can go do the quiz. Which again, maybe now is not the best time. Maybe you can do it later. Just needs to get done. And then you can also do the, I don't know if you've been on the website yet, but I posted on there a written review, and I also have an interactive review, like an online one. It's probably, being that this is an online exam, it's probably a good idea to at least do the online practice test a couple of times. That's something that I normally do in my chemistry class. Like after Unit 1, we have a test. Part's online and part is written. We didn't have that. We just had a bunch of quizzes, didn't we? So you guys kind of missed out on that. So, but that's kind of my staple, my calling card, if you will. Is there's always an online thing. I hardly lost anybody. So I highly suggest that you guys do that online practice test at least a couple of times. You can do it a bunch of times, but at least doing it a couple of times will be good. Some of the same questions may appear in our exam. Honestly, I'm not even sure because I just have so many questions online for these things. I've kind of even lost track of what I have anymore. I don't know where I am. Here I am. Okay, so I think that should about do it. Hopefully you guys stuck with that. I tried to record that. I think I blew it though. Oh no, I recorded it. Yay. Stop recording.